cloud. All right. Welcome to this review session. I put up the Slack channel with things that we will cover. There's going to be a few things here to happen first. First of all, folks have asked about the structure of next week. And so the first thing I'm going to do is I'm just going to bring up the schedule for next week, because there are a few things there that have not been explained yet, like what is this thing. And I want to make sure that as you go off to your weekend to rest from all this, you have a sense of what happens Monday morning and then subsequently. So let's actually just start in sequence here. Hackathon pitch session. So we haven't said much about this hackathon pitch session. And that's because the structure is actually fairly simple. It's we're going to all be together in the Alder auditorium and the relevant Zoom room. And you all can come forward. We'll have the handheld mic and we'll ask you to come forward or to, share, turn on your camera and unmute yourself to present ideas for things that you would like to pursue over the course of next week. And it could be very concrete, like I know what the data set is, I know what the things I'd like to do with the data set are, and I have sort of a sense, or it could be very, very vague. Both are completely fine, so long as you're sort of ready to do the next step from that either very concrete or vague idea, and you're happy to have people come along with you. Okay, and then the next part here after that, when we go for that coffee break and come back at 10:30, is going to be probably the most weird, chaotic part of this whole thing. We'll set up 6 of these owls throughout different spaces here, and we will ask you to coordinate with others via Slack to where you will go. So, there'll be the people who are leading this will be the people who are standing up there and proposing ideas. And you will have to serve as a point person to say that's something like, we're going to be in Alder 106 and also in room 3. And I'll help you with what is the match between rooms in the space and rooms on Zoom. We'll make sure that that's perfectly clear by indicating that on the Zoom links thing, right? We'll change the names of the Zoom links so there'll be a label. And then later in the week, we'll change those labels to be not like this room or that room here in the space or so on, but like the group working on, implementing registration in Julia, right? That's just from things I've seen people chat about, right? So we'll have clear labels so that when you go to Zoom, you'll know what to click on, and you'll have an owl, you'll sit around that and work with people who are here and Zoom and so on. So that first part will be a little bit of coordination effort just to find the other people who want to work on similar things to you. But then, you'll start brainstorming and you'll start coming up with ideas and start programming and analyzing and drawing things on whiteboards here and in virtual spaces and so on. So that, and it'll take a while to get off the ground. And as you find that you need certain resources, like, oh, I need a bigger computer, oh, I need some storage, or I need this data set, you'll tell us and we'll help you get all those things.
Are you recording? You want to record?
I am recording, yes. Okay. Thanks for reminding me. This is, this is something, the previous years we had a person working with us called Jane, who was always reminding us to start recording. And she actually left the university now. And so we always need the inner Jane to come, whereas in our case, maybe someone in the room. But it's okay. So I sort of explained how the hackathon is supposed to get started. And that's the most terrifying moment for me in all of this, is that moment on Monday morning. I'm always super worried that nobody will propose anything. And then we'll just sit and stare at each other for the rest of the week. But somehow that hasn't happened yet. Maybe this will be the first time. Who knows? So I have something to worry about for the weekend. What questions do you have about that? Yeah.
We don't need to prepare slides or anything.
The question is whether you need to prepare anything for your pitch, and the answer is you don't necessarily need to prepare anything. It'll be pretty rapid, and in my experience, actually, most of the time there are a lot of people who want to pitch, so we'll do this a little quick and dirty, right? We'll make a list in some Google Doc or something, and so it doesn't need to be very fleshed out in terms of preparing slides and so on, but just like a pitch, right? Like a 2-minute to 5 minute like verbal pitch.
How big are the
Yeah, go ahead.
You mentioned previously that the teams should be about 15 people max. So I wondered, and you just mentioned that you'll have like 6 distinct spaces.
Yeah.
So is it that you were aiming for about 6 teams? And what?
Fair question. The question is, okay, we have 6 spaces, we have this many people, we'll have this many projects. How is this gonna work out, like logistically? How are we gonna do? And I don't exactly know the answer to that. I will say we have had in past events that we've had here of this kind, we did have one year like a group of maybe like 20 people. And what ended up happening was that they realized that they were very good at self-organizing. I could never come up with this. They figured out that their problem slices up neatly into several sub-problems and started distributing the work among them into subgroups. So I think it's very hard to hack together in a group of 20 in any coherent manner. In which case, you start seeing like, oh, this group can work on this thing, this group of people can work on this thing, this group of people can work on that thing. In terms of owls and spaces and so on, potentially what might happen is that we will kind of like reorganize. We'll say, oh, look, this group of people is mostly people here in person, or this group is mostly people who are on Zoom remotely. So you don't need an owl, let's kind of move you around. So there would be, I think, in addition to the usual, like, where do we sit kind of adjustments, there will be like, how do we do among all these different combinations of people, how do we best organize? And we'll figure it out.
And the follow-up question, is there like a minimum size of a team that makes sense?
The question is whether there's a minimum group size. And we've definitely had in the past groups of 1 happen. Sometimes when someone just has this crazy idea they just want to explore on their own, but it's in my own very biased view, maybe less fun. So it can be anything from 1 to 20. I've seen everything from 1 to 20, and anything in between can work. I think you can make it work. It's very, just because the definition of what you're supposed to do is extremely vague. Necessarily you can do, there's a lot of different things you could do. The kind of combinations of people and how many and so on, it can also be very vague. I know it feels a little kind of like, what are we supposed to do? But maybe let's just enjoy that feeling for maybe a few hours on Monday together and see where we find ourselves. Is that a satisfactory answer? Maybe it's not. We can also live with the unsatisfactoriness of that answer.
May I ask a question?
Yes, go ahead, please.
I may know the answer, but anyway, could anyone be in more than 1 group?
The question is, could I hack on more than one thing? And I'd recommend against that, primarily because it'll be too many things to keep in your head, and also because these hack projects tend to have like their momentum, and if you're sort of well coordinated with the people that you're working with, that tends to work out a little bit better in my feeling. But on the other hand, if you're working on something and you're like, first couple of days you work on that, and then you talk to somebody or you hear about another project, or you're following the Slack channel for some other project, and you're like, oh, that also sounds like fun, I think I might switch over there. That's perfectly fine too. And nobody should feel like hurt if somebody is like, oh, okay, that was fun, I'm going to go do that over there. And I've done that even on like one-day hackathons. I tend to do something like that myself. I'm pretty bad at sticking to it. So it's doable. You had a question here in front before? It was answered. Yes, okay.
If you have a specific idea that's not sure what especially like at university, could you stage like what you do, like what question you're interested in answering?
Yeah, the question is, could the pitch be, I want to understand, I want to answer a particular question. I have no idea what methods or data we would use to answer this question, but this is the thing that I would like to understand better this week. that could be a good pitch, provided that somebody else knows at least how to get started and could really take off. Or it could go nowhere if it's like the question is like, intractable for some reason, or nobody here knows how to answer it. And then so don't hesitate to pitch something like that, but take into account that you might find yourself then joining another group later in the day. That's fine too. Yes.
Yeah, I always don't fully know my question is, but it's kind of along the lines of, what if you pitch something and either like no one joins or like some people join and then you pitch someone else's pitch, you're like, wait, that sounds like way cooler.
Yeah. What if, so the question is, what if I pitch something and somebody else's pitch is more appealing to me? Two things might happen here, and both of them are totally fine. One, you and everyone else gravitate to this other cooler thing, no problem. Or you gravitate and some other people think your pitch was cooler and they run with it, right? That's also not a problem in this scenario from your perspective. So, and I've seen that happen. I actually have seen people like pitch something, then a group comes together and then they're like, I want to go do that. And they're like, yeah, go do that. So I think that's fine. Could happen. Okay. Good. Let me, and we'll be able to answer a lot more of these questions also on Monday morning. We'll set this up and then we'll turn this over to you to ask more of these questions. So if you come up with more of these things, definitely Slack us for more clarity on that as you think about this over the weekend. Definitely go into the Hackstorming channel and just write down ideas. Really, you're not committing yourself to anything by writing down a cool idea that you have. So that's clear. Let me move on here. So that kind of covers most of this day. There would be breakout sessions. I'll just say another word about the breakout sessions. The breakout sessions are sessions where you break out from the what's going on, which is the hacking, and you go off to some room to discuss something or to hear about something or to learn or to teach or something of that sort. And that can be, we're offering a few of these should I do this? There is a schedule somewhere. Here it is. It's actually linked in the breakout session. That's a link in the breakout session Slack channel to this thing. It's just a table that says like, here's what we're going to do in Alder Auditorium on Monday at 3:30. Here's what we're going to do here in Alder 103. On Tuesday, Kendrick's offered a lot of different topics and I think, if you're interested in any one of those topics, you just drop in. And if you're not interested in any of these topics, then you just keep hacking. Okay, that's the idea. It's not like it's not going to be like now when I gathered you all from your coffee here to do this. Instead, we're just going to announce the breakout sessions are starting. And then if you come, you come. If you want to keep doing what you're doing, keep doing what you're doing. And then you can add in here other things in these slots. And there's a lot of rooms in this space. So if we need to add more rooms, I've put 3 here, assuming maybe 3 parallel breakouts is something that might happen one of these days. But if we need to add another row here, we'll just add more rooms in as necessary. And then what will happen if you're working in that, if you happen to be working in that room, we're kind of like going to shift you out, move you to the big space here in the middle, maybe move some owls around. We'll see what happens. Okay, and the breakout sessions, again, they can be any topic that interests you, that you think this would be a good forum for discussion. You can all propose topics for conversation, not just like somebody stands in front and teaches. But take advantage definitely of the fact that, say, Liberty and Dora are coming next week. Hendrik's going to be around. JB is going to be around for a while longer, right? Yeah, and Adina is here, so she's going to do data Latin. So, these folks that you've heard from, some of them are coming and some of them are going to be around still, and they can offer, we can even, if there's someone in particular that you want to come visit us by Zoom, we can ask and see when the timing works. For example, we'll have Taylor and Melanie coming for this bids thing via Zoom to talk about bids, how to contribute to bids, how to get integrated into the bids community, and I'll be there as well. I should just mention Melanie and I are on the steering committee of bids, and Taylor is a core developer, a maintainer of bids, so we have a lot of familiarity with the procedures of that, and so you can ask us lots of questions about bids, and we'll give you some ideas. So that's the breakout sessions. And there's one slot for that every day. We just want to kind of like put it in a particular corner. There's the lightning talks. We haven't said anything about the lightning talks, but we will say more about the lightning talks. The lightning talks are for you to give short talks Again, we'll be in the Alder auditorium and the Zoom, and we'll do just like we did now for the data showcase. We'll have like 5 to 10 minutes, depending a little bit on how many people are interested in doing this, to talk about something, anything that you think would interest people, either by sharing your screen on Zoom or by sharing your screen on Zoom and well, in both cases, by sharing your screen on Zoom and giving a talk either into the microphone or into your computer's microphone on Zoom. So that's lightning talks, and that'll be on Tuesday, and we'll provide more information on how to sign up for that. I need to organize how to sign up, but it'll probably look a lot like this. So it'll be I'll provide it. Yes.
Are there, off the top of your head, examples of like previous types of lightning talks that have been given for kind of context?
Yeah, we had this like in previous years, and people talk a little bit about their own research or about like a toy project that they have, some software that they like, not even software that they themselves have developed. Like, oh, there's this cool software that does data analysis for neuroimaging that I love and I want to tell you about, but just like very short, right? So it's not going to be like a tutorial on that. Because if you want to give a tutorial on some software that you think people would enjoy, then a breakout session on that would be great. But if you just want to be like, look at this cool data visualization tool, that's a great lightning talk, or something else, very broad. Just or here's this cool research that I do, or a toy project, or somebody else in my lab works on this cool thing that you need to hear about. So that's the lightning talks. That's fun. We will have a panel on careers in data science and neuroimaging. So we'll have several people, some of whom work in neuroimaging, some of whom started their career in neuroimaging and then are doing other things now, and they can tell you how they got from point A to point B. And they're all people who work with broadly in neuroimaging and data science, and have some link with neuroimaging and also with neuroscience in their sort of career trajectory. It's the kind of conversation I have with people also kind of on coffee breaks when I hear from them what they think they might do in the future with what they're learning here or in general. And I think it's good to have that conversation a little bit more formal and have people tell you from like the perspective of maybe like 5 years from where you are now, or 10 years, or maybe like 20 years in at least one case here. So so that's that panel, and that'll be in the Alder auditorium and corresponding as well. One more thing to point out are these morning stand-ups. So morning stand-ups are an opportunity for us to just catch up with what you're doing, and we'll go kind of like group by group, and each group will report out 5 minutes what they're up to. We'll do this here in this big Alder Commons space. There will be a corresponding Zoom room for that as well. We'll just stand around with the microphone and pass that around, or somebody will unmute with themselves. There's a projector as well. So that will be done standing up. That's why it's called stand up. It's a common sort of format for meetings that are done standing up so as to keep them short and snappy. Okay. Then finally, hack presentations here. We'll talk about that next week because that's a long time from now. I will mention just this farewell event for folks who are here in person. We will walk down to the water over by the Water Activities Center and board a boat that will take us on the water for a couple of hours and enjoy the Lake Washington. Not sure if we'll have reception for Zoom from there, but we'll figure out a way to do. We will need to figure out a way to do some kind of event that will involve everyone. So we'll think about that before next week, how we do that as well. Okay, I think I've talked enough about next week, unless somebody has like a burning question. Okay. Let me go then to the first topic that I will cover here, which is not necessarily the most, oops, you don't need to see my email. Not necessarily the most popular, but it was one of the most popular ones. And we agreed that I would cover that first so that Noah would cover deep stuff about deep learning later in his session, because that was popular there. And so after I cover that, you can get up and move to the other Zoom room or the other, and hopefully you'll get both of those things if that's what you want. I will go to this this webpage here, because it's justified, but also just to tell you about this, there's this book that Talia Coney and I wrote about neuroimaging and data science, and it covers a lot of similar topics to the topics that we cover here. And the reason that I'm pulling it up now is that it contains a chapter that I will roughly talk about here, which is about sharing code with others. That was the topic that folks who were interested in, is like, how do I build and structure a Python library that I can share with others? Well, what are the components and how do I get to that point in the first place? I think that's also an important question, is that we work a lot with these Jupyter notebooks, and Jupyter notebooks are great for exploratory data analysis. We kind of explore things, but there are some trappings there, right? I work one day on a Jupyter notebook, and then the next day I come and I make another Jupyter notebook, and I sit there and I code, and I'm like, oh wait, I need code from this other notebook in here. I'll go over there, I'll copy that, and I'll put it in here, and I end up with this duplication of code in multiple places. Maybe I write some functions and I have one version of the function in that notebook and another version of the function in that notebook. It's really not so great. And so one of the patterns that I find myself engaging in, and I think currently is maybe the kind of the way out of that, is to identify reusable code in a notebook and put that into a Python module, and then import that module from all the notebooks, and then ultimately, so I'm going to give you sort of the whole trajectory here, ultimately organize that as a library that I can install on multiple different machines and that others can install on their machines. And before too long, I end up with sort of a fairly standard structure for Python libraries that are shareable, installable, that have multiple components that characterize well-engineered software. And so this chapter so the link, I'll post it here to our Slack channel here. This is in particular the chapter that pertains to that and walks you a little bit, kind of text a little bit more. So I'm trying to, in one sense, I'm trying to give you like, okay, read this whole thing, and that explains this process. And on the other hand, I want to at the same time also show you what the end result is, so that so I can talk about what are the different components that the software needs to have. And there's actually, because I've given this also as a tutorial, I think the code that is in here is also in a GitHub repo that has all the components. So I'll open that here and I'll show it to you. It's called geometry, and it does the result of this whole process is code that calculates. Oh, I should make this larger. Here. Oops. Okay. Sure. Is code that calculates the area of a circle given the radius and the circumference given the radius, right? So it doesn't do anything very sophisticated. That kind of by design, in order to be able to highlight not specifically some complicated code, but really elements, and this has most of the elements that you need in order to be able to share this code and install this code on various machines. And so the chapter, and this is something you'll need to read in more detail. I don't think I can go through all this in detail today, but the chapter will show you how we go from first of all, from code that is in. And let's say that I'm doing some calculations and I'm calculating circumferences and area from some data that I have here, calculating blobs. This might be what it looks like when I write them. This was what it might look like if I write it in a notebook. I should make this larger too. It'll interweave necessarily when we write code in the notebook, and you've seen this in all the notebooks that I've shown you this week. Necessarily, it'll interweave some imports of functionality from other things, some interactions with the file system, some kind of data munging maybe, such as it is, and then some math, and then some other data munging, and then some other interaction with the file system. And this is typical for notebook code, that it kind of like goes through this whole thing. But this violates principle of software engineering of the separation of concerns, that we want different parts of our code to really separate different kinds of concerns here, interactions with the file system and the math itself and data munging. We want those things to be neatly separated from each other. And so one thing that I end up doing, even while I work at notebooks, is to write functions that implement, for example, the math parts of this. And then I have things slightly more separated from each other. But this is still not fully satisfying, because if I wanted to use this code somewhere else in another notebook, I now need to either copy it or do something else. And then, so then I end up writing a Python file, geometry.py, and I'll put in the functions. And now as I moved from this kind of notebook code to module code, I also add some documentation in here. So these are Python functions. These are their doc strings that are formatted to the NumPy docstring specification. And those functions now live in a file called geometry.py. And for Python, if you're in a folder and it has a bunch of notebooks, and it also has a file called geometry.py, you can import that functions that are defined inside of geometry.py can be imported into the notebooks. You would write something like from geometry, or here, import geometry as geo. And if this notebook is in the same folder as that file, things will work just as though geometry was some library installed on your machine. But pretty quickly, you'll want to add additional functionality and start to modularize things. And at that point, you'll want to probably move from what's called a module to a package. And so here I demonstrate this. This is a tree representation of my file system. My notebooks sit up here. And now the code to do geometry in circles is inside of a subdirectory called geometry. That subdirectory has this file dunder in it. Dunder means double underscore the name and then double underscore. It is a common sort of thing that Python uses, that annotation. Two underscores before and after a word is a common annotation for kind of like internal machinery in Python. And so there's a word for it, it's a dunder. So this is dunderinit.py. And that file, what it does is it tells the Python interpreter that this folder in which this file is saved is a Python package. What's a Python package? It's a place in your file system from which you can import names, from which you can import, for example, the module circle, right? So from geometry, I can import this circle module that contains my functionality. And then circle has, for example, a function called calculate area, which takes a radius and calculates something. And I could do some additional things with that, but let's just move a little bit further here. If I want to go from something like this that is a Python, this is a legitimate Python package. The problem with this Python package is that it's only visible right here in the file system. And let's say that I have two different projects, and in both of those projects, living in two different directories and two different repositories, I want in both of them to be able to access the functionality that's in geometry. Now I need some kind of machinery to put this code in a place that Python would always find it. And you can put it in various places. There's a variable in your shell and in your environment called Python path. And the Python path contains a list of the file system locations from which Python can import packages, right? So if we added this location into our Python path, we would be able to, anywhere in the file system, run Python and then run from geometry, import circle, and it would find this because it's in its Python path. But the problem with that is that adding various locations on your file system willy-nilly into your Python path is not a very scalable solution. If you move to another computer, now you have to sort of figure out what the Python path is there. It starts getting messy pretty much from day one. And so there's a whole machinery devoted to managing this whole thing on whatever computer you're sitting on. And the main tool in that machinery is a file called setup.py that you might have seen in Python packages if you interacted with Python packages. So now the structure of my code has gotten a little bit more complicated. I have a top level folder called geometry. Inside of that, I have a subfolder also called geometry. That one still contains my init file and then my code inside of a circle.py file. And then I have a file up here in the top geometry folder. I have a file called setup.py. And that folder should at the very least contain something like this. This is now the setup file. So just to step back here, this whole machinery is managed through a library called Setup Tools. It's a library in Python that knows how to do things like put the code in a place where Python will find it when you import it. So we import this one function called setup and the other function called find packages. We do some things. Let's assume that we have a README file in here as well. So we read that and we put that inside of a variable called long description. And then we call this function setup and call this function with a variety of metadata about our software, right? For example, it requires the pandas library. Installing this library requires that you have pandas installed. So I'm going to tell the setup function that. It requires a certain version of Python. So I'm going to tell it that. This one is important. That's what I was looking for. It has some packages. What are the packages? It's that geometry package inside which the code is. And I use this function find packages to automatically look in the file system and find folders that have inside of them a dunder init file or some such indicator that that's a package, and kind of swallow that up into the library as it's installed. And then there's other stuff here like who wrote this, what version do we have, and so on. What license we're using, and I'll come back. That was asked in the. So I'll come to the license and spend a couple of minutes on that because folks asked, and it's very natural to think about that when you're doing these things. Yes.
So to find packages function, we need to know software tree, geometry again.
Repeat that question, please.
Can you go up to the directory?
Here, yes.
We have geometry. And another the software called geometry, right?
Yeah, there's two folders called geometry here. It doesn't necessarily have to be this way, but it often is the case in projects that I've been involved in. This is called geometry, and then this can be anything actually, because it's kind of like the name of the directory in which this thing is stored. But this here will have to be called the thing that you want to type, import geometry, right? So this is the important geometry name, but I often find that this and this, it's confusing, right? Yeah.
Can you have separate folders?
And you can have several folders here as well, yeah. Although the recommended thing to do is to have one root here and then have your subfolders in here. So you can have sub-packages, right? We've seen this in many libraries that we've looked at where you're like from matplotlib dot pyplot import. So then they might have a deeply nested structure, and that can be very deeply nested, although that's not necessarily recommended to have very deeply nested, because then you end up with like from this dot that import something, and nobody wants to write that code. So this is pretty typical, and maybe you have one more level of nesting under that, and that's a pretty big library already. So actually, so that's it. And once you have that in place, if you type Python setup to PyInstall, Python will figure out what code do we have here, where should it go? I'll put it there, and is able to install that. That actually is the minimal structure. But I'll add one more thing here, and for that I'll go over here, is that it's not a bad idea to have a few more elements in your code. One element is in the documentation, it's not a bad idea to add what are called documentation tests. So I'll talk a little bit about testing, and I'll just show one mechanism for testing, and I'll point you in the direction of additional mechanisms for testing, and we can come back to testing next week. You'll notice that I've added, in addition to what I showed you before, I added this examples section here. And in the examples section, I run some code that exercises this code with some input. Now, in this case, this is an input for which I know the answer in advance, because it's the kind of answer, it's a very simple input. So I know that this should be pi. And I know that this here, if I do this, should also be pi, as it turns out. Is that true? It shouldn't be 2 pi, maybe. Anyway. We'll see how that resolves. I think it should be 2 pi. This should be pi at any rate. So I write in these examples, and this serves double duty here. One is that it's an example that somebody reading your code can look at and say, oh, this is how I run this code, right? I put in a number in here and I get a number out. Okay, I understand that. The other thing is that because we've written down our expectations for a particular input about the output, something else can go and read this and verify that that's what the code does, that when I run this code, I get this number. And the thing that will do that for us is a thing called a test harness. So we call this a doc test. It's in the documentation, but it also tests the software. And the software that checks that for us is called a test harness. Test harness, in this case, in this project, I'm using a test harness called PyTest, very commonly used. And PyTest, the way that it works is that it, if you run it in the root of your, let's see, let me clone this and I can show you how this works on the command line. Ooh, that's small. Okay. CD temp, git clone that thing. Oh, it already exists. Okay. I'm gonna delete it. Oh, maybe I should do this in the, oh, I don't know if we have PyTest. I'm going to do it on my machine because I know I have PyTest here. Yeah. Let me go ahead and do that. Okay, so now I've cloned it. I have geometry in here, and okay, sorry, I changed my mind real quick here, and now I'm going to go to the hub anyway. To see. Let me do it here. If I don't have necessary components, I'll install them on the fly. And we'll make sure that they are in there. Okay. Don't want that. I want it to be here. And I want terminal, and I want that to be much bigger. And I want to do git clone. So okay, so now I'm cloning that into my home in CD geometry, and then ls. I can also do, I believe, tree, right? So here's what I have in here, similar to what I showed you before. And in here, out of the see if I actually remember how to do this doc test. Oh, okay. Pip install PyTest. I'm going to install this thing. Pip is the package manager for Python. What I just did is usually not recommended and will not also propagate to your bits on the hub. So later I'll install that properly into all our environments. But for now, if I do this, ooh, yeah, it did hit that error. That's beautiful. So that's a thing of beauty. So they'll just explain what happened here. I ran PyTest doctest modules, and what this does, so this is the test harness. It's a little program in the command line, and it takes as an argument here the fact that I want to go and check the doc tests in the modules, as the name here suggests. And what it does is then it goes through and it searches for these kind of patterns. Like here's an examples with like Python code that I run, and I ran that function with this input, and this is the output that should happen. And so for each one of these, you'll get one of these dots here. And if it hits a failure, if it hits I expected to get this, but I got this instead, it will raise this kind of failure. And that's a good thing. We want this to fail because this is the wrong answer here. And that lets me then go and edit what I have. Go and edit and put in the correct answer instead of this wrong answer. Save that, and then go back here and run the test again, this time coming out green, right? So this is and now, in this case, it's very simple, but if you put a lot of these into your code all over the place, covering many, many use cases, and then you start changing stuff in the code as you're working, you have this kind of insurance. Every time you'll want to run this thing so that you can make sure that because code gets really complicated and you start having things depending on each other. I edit it over here. I want to run the test on the code over here to make sure that it doesn't break when I work over here. And this, if I have a lot of this testing, I can kind of get that covered for me. Yes.
There's a different formats for the doctoring, like Google has one.
Yeah.
Does it work with different kind of formats?
It does generally work with, so this kind of doc testing does work, I believe, with different formats. I'm very, very conscientiously using here a very particular format called the NumPy docstring standard. And that's because it works well with other kinds of tools. So it has really this, like the fact that there are this number of dashes here, and this is called parameters with a capital P, and that there's a space on this side of the colon and a space on this side of the colon, all are intentional choices. So there needs to look exactly like this and not otherwise. Primarily, there's other code that will take this and write, for example, web pages that contain the documentation of this, and they rely very much on this formatting. So that's another element that you can add to your code, which is documentation. We have these doc strings, but maybe you want a nice manual about your code. I won't go into detail about documentation today, but I can show you various ways to go about that. What other questions do you have at this point? Yes, another question.
Again, the precision of the outcome there.
Yeah, so this is kind of like floating point precision. Why doesn't it need all the other numbers of pi here? And that's because the testing is configured to do a rough comparison up to some tolerance, and you can set that tolerance. So yeah, this will be really important if you're doing more elaborate, and there are more elaborate ways that I won't show here, but we can talk about later to do testing. In fact, once you start doing testing, it's not a bad idea to start adding files that are strictly devoted to testing. I'll kind of show you what the pattern is. You add a folder called tests, and inside of that you add a file. This will be a Python file called test circle. So this name, again, test underscore the name of the module that you're testing. And in here you will write, and I won't write it in detail now, things like def test calc area. That here I'm not writing this, but run some test code. Well, actually, why not? From geometry dot circle import calc area, and then assert that calc area of 1 equal to, it's calculator. Right. So here I've added a few more things. There's a folder under geometry called tests. Inside of there, inside this folder, there's a module by itself called test circle. It's devoted to testing the functions that are implemented inside of that particular module. I'm testing in this case. These things have to be called test underscore, both of the file and the function, because PyTest will go and it will look for. Let's see if that actually works now. When I run this, it will now look for, it worked. It looks for files called test underscore something, and inside of those, it looks for functions that are called test underscore something. And this is something that might be unfamiliar to some of you, is the assert statement in Python. What it does is it looks at the Boolean value of the thing that comes immediately after it. And if that is incorrect, it raises an error. Well, let me demonstrate that. And then this other thing over here is what it will say. So let's say that instead of doing that, I said that by mistake, then it will say, oh, you had an assertion error, wowza, because that's the string that I entered there. And it's because, I got this, but you told me that I should be getting that, where this is this thing. So now it fails in this particular way in here. And now I fixed it, and now it passes again. So it tells you again, I've tested the two docstring, the examples, these doc tests inside of the function circle.py, and then I ran one test also in here. I got 3 tests passing. This is how long it took. And so now you can write a lot more tests in there, right? Because inside of here, you can write a long list of different use cases for your code and test all of them in this way. Yeah. Okay. And it's a good idea to have lots of that. Yes. More questions?
Last one, I hope.
Yeah.
Can you connect this test somehow to the GitHub and do a breakpoint on that?
Okay, so let me show you. So okay, this becomes a little.
This,
So the question is, can I somehow connect this to GitHub? And I think what implicitly underlies that question is like, this is pretty cumbersome. Do I need to go and run this every time? Like I'm making some change. I need to go to the command line and remember to do this. What happens if I forget to run this every time? I change the code, it goes to GitHub, I committed it, and now somebody else downloads it, and now their tests are failing. How do we avoid that? And the answer is called continuous integration. And it's a good reason to go back here because continuous integration is in fact implemented here in the form of what are called GitHub Actions. So the GitHub Actions is a system on GitHub that will take our code, download it, install it, and run our tests for us. And then so when I push to GitHub, it runs the tests. And if the tests are failing, I will get a little X here. And we know why this X is here, and that's because I changed that that thing that was supposed to be 2pi is pi, so that's wrong, and that's why it's failing here, and I'll show that in just a second. It's always stored in a folder called .github/workflows. Inside of your code, you will have a folder called .github, and that will have another folder called workflows. And inside of that, there will be a configuration file written in the YAML markup language. And here it is. It's kind of elaborate, so I won't go in detail into it, but I'll just kind of point to the steps. It kind of checks, when should I do this? Oh, when you push to master, or when you make pull requests against master, then I run this thing. What I do it on 3.6 and 3.7. I check out the code. I install the dependencies. Here I'm installing Flake 8 and PyTest, which are dependencies for testing this. I run this linting. Flake 8 is a linter that checks that the coding standard is compliant, like I have spaces in the right place and so on, things that Russ talked about on Monday. Remember Monday? That seems like so long. So I run that here. That's the linting, and then finally I run PyTest, doctest modules, and I point to the module that I want to test geometry. But you could live with that, with or without that, I believe. Maybe not in this case. Anyway, this is the whole configuration, and then if I go to the actions, you'll see a little bit of what happened here. This is kind of the interface, and you can go click in here, and it will show me. Oh, they've expired, because it's been a while since I did that, but it'll show me kind of what it would show me if this was not pretty long ago, and we can set these up for you and look at those. It would show me how each step of these steps ran and when exactly that failure was raised, and I will in fact get a view just like this one, because PyTest will have run on some machine, and they will show me the logs from that machine in that window, showing me the specific failure that existed there. Let me see if I can just push this. Git status, git add geometry tests, git add geometry circle, git commit -n added tests, fixed, broken tests, and I will do something that you probably shouldn't do, which is I'm working on the master branch here, and I'm gonna push straight to master here. Git push origin. Oh, it added some things that I didn't want it to add because why? I'm not sure. Oh, it's inside of tests. I don't like this. Git rn geometry tests .ipynb checkpoints test circle checkpoints. Git status commit and remove craft. And I'm pushing straight into master here. A dangerous thing to do, but this is for demonstration purposes here. And so what will happen here is that this will turn orange because now it's running this thing. If I go here to the actions, you'll see that there it is, remove cruft that I just pushed. And if we're going here, it hasn't completed anything. Let's go to the build. It's building it on 2 different versions of Python because why not? It's already set up the Python. It's installing the software right now. Oh, it's running into some errors. Okay, it had some issue installing the dependencies. That's too bad. This is long and annoying. It requires 3.8, and I asked, okay, let's. Sorry, I'm gonna fix this. It's fixable, I believe. I know exactly where to fix it. It's in my setup.py. I said require. Oh no, interesting. Okay, I'm not sure what's going on. So I'm gonna ditch this. But anyway, once I fix this, it does all these steps, and the nice thing about this is that if somebody else goes and downloads the code, they will likely run into this. So I got now an angry email from GitHub saying you ran this action and it failed, go fix it. And that's much better than assuming that I will run the tests every time. And the nice thing about this is that if I wasn't living dangerously and I pushed to a branch and I made a pull request properly, that pull request would have failed. And if somebody else was also reviewing my code, they wouldn't even look at my code because they'd say, fix this failing stuff before I even take a look at your code. And you can go like that for quite a bit, fixing all these things by yourself. You and GitHub going against each other until the code works. And then finally, somebody can go and review. And that also, we talked about code review the other day. It's like, you don't want to have to download everyone who makes a pull request, you don't want to have to download all their code, test it locally on your machine and see that it works. You want it to be installed into like a very reliable, well-configured environment and run there before you even look at it. And then you can do things in the review, like say, you haven't tested this functionality, please add a test for that and see that that passes in the GitHub Actions.
I have a very general question. So Jupyter notebooks are really beautiful and easy. Let's say that you want to work on a Docker container, and I'm wondering if we can work on developing some container inside these notebooks. Because at the end, you want to test your Docker by actually pulling up the terminal mounting thing and like actually pulling the software packages, the bag, and run it on inside your terminal.
Yeah, so how do we sort of interact with Docker in here and so on? There are ways to build. GitHub Actions can run Docker in the sense that they can automatically build for me. I do this all the time, actually. And we do this, the way our Jupyter Hub is set up actually is through, I'll show it to you, a GitHub repo here called Hub Image 2022. It's public, so you can view it. It's got a GitHub workflow, and it does some workflows here. I can show you, for example, just this morning, we added some dependencies for Liberty's lecture here. And then it went and it built a Docker container here. Here, build and push the image. So here it's building. You can see that it's running some Docker command that's pretty elaborate and long. It does all the building up here and then does lots of stuff. And then in the end, it pushes it to, in this case, not Docker Hub, but Quay.io, which is another Docker registry. And then somehow our Jupyter Hub knows to pull that Docker image, and that configures all our environment in there. So this is done through GitHub Actions as well. And you can automate that. And the next step can be, instead of pushing this up, can be, please run this Docker image here with the following data, right? Download some data in here, run it. And seeding some ideas maybe for hacks, you can do this, maybe you can run it multiple times with multiple different inputs or multiple different configurations and store all of those results. And then you get yourself an automated multiverse analysis or something like that, maybe. Yeah.
So did you write the GitHub action file or code, or is that something that it generated?
In this, no, both could happen.
Okay.
Yeah, there is. If you start a new GitHub repo, you go to that Actions tab. It'll say something like, "You don't have actions here yet, but this looks like a Python repository. Here's a Python action you might want to have," and then you start from something that they give you, and then you start editing it. But you can edit also, or you can write it yourself. I've never written one of those from scratch, though. I've always copied them from elsewhere and started tweaking.
Maybe somewhat related. So I noticed when you were adding files one by one, if you've got like a nice git ignore set up. Is there any reason not to just git add and then put the top level director like in a period?
Oh, I see.
Is that,
Yeah.
like, is there like a best practice against that?
Yeah, the question is, so this is sort of to Git a little bit, you could put a git ignore in there that would ignore that checkpoint file that I had to struggle with for a little bit. And the question is there any reason not to say git add star in here, go like git add everything and then commit? It's not generally good practice because you want to know what you put in there and check with git status, but I'll just mention that there is a real shortcut to do that. If you happen to want to do that a lot, if you did git commit -am, then that's like add everything that's currently changed, right? You don't really want to add everything. You want to add everything that changed since last time.
That's why I was wondering. if
Yeah.
it's inefficient.
So you look at this like this git status, there's good reason these things here are untracked. So you don't want to add those, but you do want, if you've edited multiple files and you want them all to go together into one commit and you don't want to add them one by one, git commit -a and then m and then the message will add everything first and then write the commit message and make the commit and then off you go. So this is something, honestly, this is something I do a lot. If I do git status and I see, oh yeah, those two files are the code and the test corresponding to it, they should go together into one commit, then it makes sense instead of like writing multiple commands there to do. Okay. Yeah.
Is that you just said the same thing as doing like git add dot and then git commit in two separate lines, or just doing it in one?
No, the reason it's, so the question is if this is equivalent to writing git add dot and then git commit. The reason it's not that is because if I did git add dot, it would also add this other cruft in here. I don't, it avoids adding things that that are currently untracked. If I had the git ignore, so that was the question, how the question started. If I had git ignore set up nicely and I was immune to all these untracked files here, I had no untracked files, then yeah, then it would be equivalent actually. It might complain here, it might say you're trying to add this thing that you told me to ignore. So it's not exactly the same, but in that case, it'd be like functionally equivalent. Okay. I'm going to shift over to the other thing that was also pretty popular. If you want to hear more about deep learning, you can go to the Alder Auditorium and the equivalent Zoom, and I'll talk here about ridge regression. I believe that was the other thing that was pretty popular here, but I'll check again. Yeah, that was the most popular. Sorry. So we'll talk about that for a few minutes here. I'll try to go back to the machine learning tutorial and basically walk through. What am I walking through here? Yes, notebook number 5. So this will be a little of a drawing shift here to model selection. So, okay, before this point in the tutorial, so just to rewind you to a few days back, before this point in the tutorial, we talked about the fact that we can cross-validate, that meaning we can set up a particular model and then fit that model to some data and then test whether this particular model in that particular setting fits some data, some test data that I left aside, whether it fits that well. And I could do that for multiple different settings. We did something with like the number of samples, right? You increase the number of samples and you see that the model, kind of like the train tests, converge towards each other as you do that. Here, instead, what we're going to do is to demonstrate that, and here I feel like this is the point at which machine learning and classical statistics really diverge from each other, is that once you adopt this mindset that you can kind of check how the model, automatically check how well a particular setting of the model works, you can start doing all kinds of, you start learning or coming up with methods to make the models better. For lack of a better word. I'm going to skip over this variance bias because it's a little theoretical and go straight to this idea of regularization. The idea behind regularization is that in the regression setting, if we're fitting a linear model, we sometimes have some prior knowledge about the nature of the model that we would like to fit here now. And one way to think about that is that we might think something like the following. So this is the standard cost function for linear regression. It's the residual sum of squares. This is the y, this is the age, for example, in our age prediction model. And this is the product between the beta, the coefficients on each column, and the values in each column for a particular individual. And so this is a linear sum of the areas of different brain regions and thicknesses and so on as we fit in the model. So for a particular setting of beta, this gives me an estimate of y. This gives me the true y. I'm summing and squaring, and that gives me the residual sum of squares, the error of the model. But I could also say, given what I know about the world, about this particular thing, I would like the cost for fitting this model to be the residual sum of squares, but I would also like at the same time that the sum of these coefficients be as small as possible, or the sum of the absolute values of these coefficients to be as small as possible. One way to say this is that I have some prior knowledge that the model should be as sparse as possible. Sparse meaning as few of these, as few of these should be active. And I have a hyperparameter that tells me how much I'm balancing those two. If I set this lambda to 0, that's just the standard linear ordinary least squares. If I set this lambda to a very high number, then I actually don't care at all about these residuals. I just care that I just want the weights to be 0, or I want the weights to be as small as possible, meaning I will set all these weights to 0. So this lambda, this value of lambda, is not a parameter of the model. Instead, we think of this, because the parameters are these betas, instead we call this a hyperparameter. That is, it's a way that we fit the model. It's not what we fit when we fit the model. And this cost function is implemented in the method called the lasso. There is another one that we'll look here at shortly, another regularized regression method called ridge regression. It's actually much older, and it has a slightly different penalty. So this is the residual sum of square again. This has the penalty that the sum of beta squared, not the absolute value, but the beta squared, should be as small as possible, also parameterized through a hyperparameter called lambda. So these are two different ways to implement different kinds of sparseness. Sparseness for the absolute values and sparseness for the square of the values of these coefficients. Yes, question, Mike?
So if you set the lambda high like that, would that be the equivalent of like a null model or an intercept only model?
Yes, yeah, you could think of that as like, because what would effectively happen here is that all the coefficients would go to 0, and you would be predicting the mean every time, right? And we know already what the R squared for that model is. It's 0. That's what the coefficient of determination for the null model of the mean is, the R squared is 0. So by setting lambda, so that's a pretty bad setting of lambda. On the other hand, if you go too far in the other direction, you're prone to overfitting. In particular, if you have more coefficients than measurements, you're always going to overfit. If you just let beta be whatever it has, that we showed that, right? As you add more and more columns, you end up with an R squared of 1. And so this pulls you back from that overfit model to give you a model that effectively has less parameters and gives you a better solution. That's one way to think about that. Yes.
Sorry, quick question. Is
Yeah.
lambda bound?
Lambda, in theory, it's not bound. No. I mean, I think it needs to be positive. Otherwise, weird things start happening. But
To make an intercept model.
it can be anything. Another self-promotional. This is the paper that Kendrick mentioned in his this is the software that Kendrick mentioned in his talk about NSD. This is a method that mostly Kendrick, and I developed to find a reasonable range of lambdas to use, which is a good thing to do, because in principle it's not bound, and people will do things like, let me use lambdas on a log scale. Let me try 0.1, 1, 10, 100, and 1,000. And so we came up with a rational way of doing that. No, it's not. It's, we haven't reached whatever the threshold is, 1,000 citations or whatnot yet. Any day now. Any day now. It's also, yeah, we can talk about it more. I feel like it hasn't been broadly accepted yet as a method. We think it's great, but some people have objections to it. And there are multiple other methods to do these kinds of things. So I should say there's a whole world of these kinds of things. So it's hard to imagine that all of those things would be in scikit-learn. But it's scikit-learn compatible. So if you have scikit-learn pipelines, it will work with those, no problem. Okay, and we have 15 minutes. So I can kind of show you how this plays out in kind of in the real world, in some real data. Let me just make sure. Did I read that? Yeah. Okay. So let's look at these ideas a little further. I'm going to implement some function here, and then I'll explain what this function does. I'll run this here, and then we can talk about it. So here I'm fitting a model. It's a lasso model. It's got 200 features. So I'm starting with 200 features. And then I am going to sample 200 columns. And I'm going to use a log space, as I told you, for these alphas. We call it alpha here, not lambda, because lambda is a keyword in Python. So instead, it's called alpha, just to confuse you between the math and the code. And here's a figure, and I'll explain what this is. Each line here is the value of one of these betas. And on the x-axis here, I have the penalty, the value of alpha. And then on the y-axis, I have the value of that coefficient for that level of the penalty. And the important thing to notice is that over here, when the lambda, the penalty is very, very small, the model really focuses on residual sum of squares, and the values of these things are relatively large. By the time we got to a lambda of 100, I guess, or no, 10, then they all shrunk to 0, and that's because the penalty on the weights was so big that they all got squished down. And over here, what we are doing is guessing the mean, assuming all the data is demeaned, I should say, or this is an intercept-only model of sorts. Along the way, there's a path. At some point, each one of these goes to 0 at some point, right? If you go from the right to the left, you can see that it turns on one feature, and then it turns on another feature, and then it turns on another and another and another. And one way to think about this is that this is a method for variable selection, because it starts choosing which variables to add, going from the right to the left into the model. Now, these are not monotonic, right? There's like this purple one, it goes up and then down and does all kinds of things. So there's more to it, really. But one way to think about it is like turning off more and more as you go from the right to the left, weighting some of the betas less and less. You kind of turn on more and more of the variables. Okay, bear with me here. This is ridge regression. Very similar idea, except now the penalty is on the sum of the squares of the betas, not the sum of the absolute values. It looks different. We don't need to actually say more than that, but there's a similar idea, right? But here, instead of turning on one by one, they kind of all come on together. That's the main thing to sort of think about, is the difference between those. But I will say the most important thing here is that you can use the principles that you saw before in order to come up with a procedure for determining what is the best lambda to use for a particular data set, a particular model. That is, you'll do cross-validation. That's kind of like the answer here, is you do cross-validation. You choose a lambda, well, you split it up into train and test. You choose a lambda, you fit the model on the training data, and you test the prediction on the test data, and you see which value of lambda minimizes the error on the test data. The full model will have the smallest error on the training data. We know that already. It has to be, because the residual sum of squares there is the most dominant. So the model furthest on the left here has to be the best on the training data. But that doesn't mean that it will be the best on the test data. There'll be sort of a U-shaped thing here, and you'll see that U-shape down here, maybe. Just run everything. Okay, run various things here. Hopefully that curve will show up. I'll just tell you, there is an optimum here. There's an optimal value of lambda such that the model is not overfit to the data, and it's also not crushed down here. This model we know is not great. So in between there's some optimal value that's true for this cross-validation. Yes, questions here in front of us.
Is it like standard to like do cross-validation between different regularization methods as well, or do you like choose a regularization method?
Yeah, so the question is whether you can compare, for example, different regularization methods like Ridge and Lasso. And yes, you can do that, right? Remember the framework that I presented here at the end for the validation, was pretty important, is this kind of like has this nested nature to it. You can do, in some sense, you can do whatever you want over here, so long as you never touch that before you're really, really done doing that. So you can do different regularization methods. You can do different model structures. You can do something non-linear. There is, in the end here, there's these fancy tree-based methods that are very different from there are other methods to predict the age of somebody based on their brain data that don't require like a linear sum of coefficients, right? Or kind of like weights on his brain areas. So you can do other things. Where is that U-shaped curve? Here it is. Okay, this is Ridge. This is Lasso. So here's the U-shaped curve. It's an upside down U here, but just to point out, here we're going, x-axis is the penalty, y-axis is the coefficient of determination, and there's the training data and the testing data. So higher here is better values. The dashed line here is for comparison ordinary least squares without any penalty. Notice when the penalty goes really, really high, the model is zero. That's what we said before. This is the over here on the left, on the right is the intercept only model. On the very left is the best model for the training data, and that's again by definition we're pretty much ignoring here because alpha is so small. We're pretty much ignoring that additional, and we're focusing only on the residual sum of squares. So this one kind of monotonically goes down, and that's by necessity. But this one goes up and then down, and does have an optimal value of, the alpha, for which that's kind of the best regularization for this setting. And this is the kind of thing that you hope to see when you fit these kinds of models that you found. And the problem then becomes like, what if this is also monotonic? You have to go outside this range maybe, and so on. And that's what part of what FRAC-Ridge solves, is that problem. So this now, I hope, gives you a little bit of a flavor of why these cross-validation methods, together with all kinds of clever ways of penalizing and optimizing models or predictions, they start becoming really powerful and give you, but also really dangerous, right? Because you can try a lot of things there, and you have to make sure that at no point does this test data down here influence your decision making about what you do over here. Because if it starts influencing your decision making in any way, then you're in trouble. For example, one way it might influence your decision making is if you look at this data and you say, oh, I should normalize the data before I start, and you normalize the data over here, including all the data. Now you've generated a dependency between your training data and your testing data, right? Because you're normalizing, taking into account all of this data. Another way that people will get into trouble is the data is really complicated, it's big, it's got lots of dimensionality. Let me do a PCA first on everything and then do that. Also, you're gonna mix your test with your train and get there. One thing that I didn't point out, but I will point out now, just as a general rule, is that scikit-learn, one of the ways that scikit-learn is really great is that it contains this notion of a pipeline. And I won't really show code that does pipelines here, but it's really worth exploring. And one of the big strengths of the pipeline abstraction is that if you include all the steps in your pipeline in the pipeline itself, it contains, for example, it contains a normalization step and a PCA step, and then some other step. In the end, that pipeline object, and then a model fit, that object by itself that combines all these steps will also have the fit and predict methods that the estimators have. And so you can do a dot fit with my data, and it'll do all the steps in the pipeline. And if you always remember that before you fit, you need to split your data into your test and train, then you'll get into less trouble. So it helps you avoid these kinds of errors that are pretty common in how you handle your data and how you kind of avoid what's called peaking at the test. Yes.
How would you choose the like the k-fold crosstalk, the k in the k-fold?
Oh, yeah. How do you choose? Well, where did this number 5 come from? And does it matter? I don't know how people choose these numbers and why, right? Because here I had 5 and here I had 10, and it needs to be, or where was it? I had an image here with 10. Anyway, I don't have a good answer to that except to say that my hope is always, it needs to give you enough, right? On every fold here, you have to have enough data to fit the model on the one hand and to evaluate it on the other, right? So that somewhat guides my, when I look at this, somewhat guides my choice, is that I want to have enough data in these validation sets here so that when I predict for them, I could get an error that makes sense, right? If I ended with 5 people in here, then it's too little, and maybe I need to go to like if my let's say my error bars, like just the variance between these is huge, then I worry that maybe those sets are too small and I need less folds. So that's a bit of a guideline, but that's still very shaky. Does anyone, maybe Jay?
Which is why you should avoid, leave one out.
Yeah,
You're basically running the same model. There's only one sample that is out.
Yeah.
So you're not exploring the dividing the data from the model.
Yeah, that's so I'll just repeat that. The extreme example of k-fold cross-validation is n-fold cross-validation, where n is the number of observation, and it's also called leave one out. Every time you leave one person out. And if you do that, then you'll get very large variance between folds. The extreme on the other end is called two-fold cross-validation, where you split half essentially. Here you leave half, and here you leave half. And that may very well be a good choice sometimes. Why would you not do two-fold all the time?
Again, it's a question of exploring there's two sorts of values, right? There's the source of the data, right? The sampling source, and then there's the source of the variation of what you do to the model. And basically the balance that you have to reach is to explore those two sources of variance. That's why people come up with 5, 7, 8, on general, because that's often a good compromise between those two sources.
Yeah, so just to repeat that, there's trying to balance two sources of variance. One is the variance in the data, that's to leave one out, and the other is kind of sources of variance. We're trying to explore different variance in the way that the model fits this, which is the pulls us towards larger K. And I'm sure that somebody's written, I can point to a book that probably has a much more elegant explanation of this and more mathematically framed. There's the folks who invented, one of the people who invented lasso, the person who invented lasso is Rob Tibshirani in Stanford's statistics department. And he wrote together with some colleagues a beautiful book called something statistical learning. Elements of Statistical Learning, and it is free to download as a PDF online, but it also comes in this beautiful dead tree form that you can borrow from the library. And it's a great book that I've read, and I'm still trying to get through the hard bone in the front of my head. But probably among the many things that didn't get through my head is probably a good answer to.
Maybe you're trying to dig 3-1.
Yeah, banging it too hard. Okay, yeah.
So I wanted to go back and make sure I understand, when you split the data, so I understand you don't want to run like a dimensionality reduction before you split, because then you lose independence.
Yeah.
So then if you do have high dimensional data, and you do a partition and then do PCA on both of them separately, and then.
Right, so I wouldn't do a PCA separately on them. I would compute the PCA coefficients on the training data and apply those coefficients to the test data. And that's exactly what the pipeline would do for you, right? let's say you're normalizing, right? It would calculate the mean and standard deviation on this thing. It would calculate the PCA coefficients on the standardized thing. It would calculate, beta weights. Well, here inside this stuff for each one of these, it would do all those things. And then it would apply all of those things that it learned. The mean and standard deviation of the training data. You don't want to know the mean and standard deviation of your validation data of the thing you're testing on. So you don't look at that at all. Just apply the mean and standard deviation that you learned from here to normalize this thing. You apply the PCA coefficients that you learned from this thing on that thing, and then you apply the coefficients of the model on this as well, and you predict without ever having looked at that thing, and definitely without ever having looked at that thing as well. What kind of applies doubly.
Can I follow up on that?
Yeah.
So for validation stage, we just like, let's say, do the PCA on the training piece and then test on the validation.
Yeah.
And you do this like 5 times,
5 times.
but then later, so you choose your.
Yeah,
let's
right.
say-
So now you've optimized this. Which
Exactly.
PCA coefficients should you use? So the standard procedure then is to take all of this stuff, go back here, and the stuff that you learned here, if you feel pretty good and confident, you apply here. You fit that, you do the normalization, the PCA, the model fit over here. You get one set of coefficients, one set of mean and variance, one set of PCA coefficients, one set of model coefficients, and use that in order to predict. And since you did this a lot and you're like pretty good, sure that you did the right thing about like setting the regularization parameters, then this should be a good estimate. And now, not only that, you got the bonus that you got the full data set to fit this on. So this, that should be the best possible model given the amount of data that you used for the training. That answers that.
When you have an hyperparameter, this is just one loop of what you usually do is actually do a nested cross-validation.
Yeah.
Right? So that train and test will actually change, at the higher level. I don't know, I mean, maybe I can do it all.
Yeah, I can just maybe kind of wave my hands here and point you to a paper that Adam, who gave a talk earlier today, did that included this kind of procedure where sometimes you have to take this and you have to do another round of cross-validation inside, like nest another one of these down below to set some other hyperparameters in there. So hyperparameters maybe, right? That's what you mean?
No, I mean just for the hyperparameters. So that's that cross-validation loop, at I would say the outside cross-validation loop, okay, is usually for the parameter, but inside each of those loops, you can optimize the hyperparameter. And that is also the cross-validation.
Yeah.
So I mean, it's maybe, I don't know if you want, but I could do like half an hour little things on the nested cross-validation and why. I'm sure there are good tutorials as well on the web.
Yeah, I'll point to Adam's paper that contains a nested cross-validation, cookie preferences, whatever. I'll send that to Slack here. And it also has a nice figure that shows like, oh, well, nice. I think it's nice because of course I do. But it contains a figure that at least explains this idea of like nested cross-validation, that you can do more levels of this kind of procedure, and it's a fine thing to do.
It can get confusing quickly.
Yeah. It's always a good idea to just put aside some test data before you ever touch anything and not come back to that data until you feel really, really good about what you did so far. And then just apply it in the end, and then you see what you see, and that's it, and that's the answer. That's what you learned. Okay, and I will thank you here. Have a great weekend. Enjoy the sun and heat and water and forests and mountains and wherever you are, whatever weather and so on. And I'll see you all on Monday morning.